and we've been talking about, got into really some organic compounds that have that carbonyl group, and a reminder that the carbonyl group, right, is our carbon oxygen double bond, right? That's our carbonyl, and it's sometimes referred to as our carbonyl carbon. And we really got into last time sort of two groups that have this sort of guy as part of their functional groups, and those are aldehydes and ketones. So we have our aldehydes and we have our ketones. And a reminder that the functional group of each of these look kind of similar, but a little bit different. First off, the aldehyde has the carbon oxygen double bond there with a hydrogen at the end. So it looks like this. Again, that being the functional group there of our aldehyde. While a ketone has a kind of 3-carbon run with the carbonyl or the carbon oxygen double bond there in the middle. So we talked about a couple of things. First off, we talked about the idea that the aldehyde group, because of the hydrogen that's here, will always be pretty much at the end of the organic molecule, either the left-hand side or the right-hand side, depending. While the ketone, because you need that sort of 3-carbon run there, you'll never find the carbonyl group there at the end. There will always at least be one inside from the end, but it can be in multiple locations. So I believe where we left off here altogether was we were going into talking about how to properly name aldehydes, and pretty much our aldehyde group are named by basically putting an AL at the end. So we drop kind of the E off of the name and we add the AL. One of the important parts, for example, if we did something like this, maybe 3 there, we would look at this and this would be 2 carbons. In this case, 2 carbons is based off of ethane. We see the aldehyde group there at the end. We drop the last part, and this is what is known as ethanol. Al, not to be confused with our alcohols, right, that end in OL, but these aldehydes will end in Al at the end of it. Now, we don't need to give the location of this, so no need for the location. And that's because of what we were just talking about. It will always be at the end. So either it'll kind of be on the right-hand side or the left-hand side of the molecule, but it will always be at the end. So you don't have to give the location. And what I mean by that is, like, when we have double bonds or triple bonds, or we have like an OH group, we typically need to give the location of where those guys are. Here you do not have to do it regardless of how many carbons, because it always should really be at the end. With that being said, though, when you do go about and number them, even though you don't give the number in the name, this obviously, wherever this carbon oxygen double bond is located, will always be carbon 1. So that's sort of important for if there's sort of other groups attached to it. They would be numbered accordingly, with that carbon oxygen double bond carbon, or that carbonyl carbon really being carbon number 1. So don't need to give the number of where it's located, but we do give it a number of 1 in terms of numbering for everybody else. Any questions on that there? Okay. So here's again some of our examples, and we can see the naming like we talked about here. We basically have 1 carbon, which is based off of methane. This is what is known as methanol. Also, we talked about a common name for that guy, which is formaldehyde. So that's a common name you should be aware of. It's used a lot still. This obviously has our 2 carbons like we just did, which is our ethanol. This has 1, 2, 3 carbons, propanol. And lastly, 1, 2, 3, 4 carbons, butanol. Again, no need for the location of carbon-oxygen double bond, but in each of these cases, that technically is carbon number 1 in case there's something else that's attached. Any questions on that? So why don't you take a second here and give the name for this guy, see what you come up with. Here, obviously we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. This is obviously the chain that has the aldehyde group, which is right here at the end. So 5 carbons is going to be based obviously off of pentane, because we see our aldehyde group here is going to be pentanal. And the other group that's attached is actually a methyl group. So although we don't need to give the location of this particular carbon, it is definitely for numbering purposes going to get the priority and going to be carbon number 1, which means really our methyl group here will be at carbon number 2. And that would then be 2, if it writes, 2-methyl pentanal. Any questions on that one there?
I have a question, Professor. So, I guess, number 2, the C, could you also write that CH? Like, could you combine the H?
You could, so if you're asking if you were doing more of a condensed structure, you could write it like this if this is what you're asking. You could put the CH like that and then the CH3. Is that kind of what you're asking?
Yeah, yes, that's what I was asking. So it's the exact same thing, correct?
It is the exact same thing. I think they just accentuated it here so you could see the group. But yeah, you could write it exactly like I just did here on the left.
Great.
Perfect.
Thank you.
Welcome. Other questions? Okay, and again, in terms of line structure here, we would be looking at something that looks like this. We got there 5, 1, 2, 3, 4, and 5. It looks probably something like this here. Again, this would be, sometimes people won't draw the H because it's implied that this is technically a carbon right here with 3 bonds. And then remember, a lone line basically represents a methyl group, and this would be carbon 1, 2, 3, 4, and 5. So line structure would just look like this basically. Question on that one there. Okay. So actually, let's do a couple more here real quick. Why don't we do so once you give that name, and why don't we do let's do 4-chloral 5-methyl octanal. Why don't you draw the structure for that guy? So let's do name on this one. Let's do structure on that one there. So let's take a look. So we just want to kind of follow our same approach here. So we'll start with the naming part. If we just go straight across, this has got our aldehyde group here. So we know it's an aldehyde. So that's 1, 2, 3, 4, 5. You also, if you wanted to, go straight across and then down would get you 5 as well. 1, 2, 3, 4, 5. Again, because really you get the same result, which no matter which way you go, might as well take the straightest there. That also shows us we got a couple of groups hanging off of this particular one here. Obviously, we got a bromine and a methyl group hanging out. So we'll start with the carbons, which is 5. So much like the other one, that's going to be based off of pentane. That's going to give us a pentanal, Al. Remembering again, we don't need to give the location of this guy here, but it is going to be carbon 1, which means that that's going to be carbon 2, That would be carbon 3, that would be carbon 4, and that would be carbon 5. That means at carbon number 3, we have a bromol group. At carbon number 4, we got a methyl group. Alphabetical, going to put the B there in first, so that's going to get us 3 bromol dash 4 methyl. Squeeze it in. There we go. Pentanal. Any questions on that name there? So like normal, going from the name to the formula, we're going to proceed backwards here. So first thing that we see is an Al, which tells us it's an aldehyde, so it should have this group on it. We see octane, basically, which is 8 carbons. So that's where we'll start with just 8 carbons. And again, like normal, I'm not going to really put much in there but the carbons to begin with. And try to count 1, 2, 3, 4, 5, 6, 7, and 8. Again, because you're drawing it, you can really put that aldehyde group on the left-hand side or the right-hand side. I'm just going to put it on the right-hand side, but you could put it on the other side. Because I chose to put on the right-hand side, that will then make this carbon number 1 for me. And that means at the 5th carbon from there, I should have a methyl group. So 2, 3, 4, 5, again, should have a methyl group happening. That takes care of that. And 4 away from that first carbon should be a chlorine group. 1, 2, 3, 4. That takes care of that. Everything else, like normal, is going to be hydrogen. Again, the goal here is to get to 4 bonds for carbon. So he needs 3, needs a couple of hydrogens. This guy just needs 1 as it has 3 lines coming in. This guy also just needs 1 because it's got 3 lines coming in. This guy needs 2. This guy needs 2. And our aldehyde group doesn't need any. It's got as many as it needs. And that would be our structure. Questions on that there? And obviously that would be our condensed structure, what we just drew there. Which basically is, don't draw the hydrogens out now. Okay, so that's aldehydes. Let's talk a little bit about ketones. Ketones, again, actually, before we get to ketones, let's just talk about something that we might come across a little bit later on as well. Let's just talk about, actually, we'll use the structure we just drew. Sometimes the carbons are named with sort of Greek letters based on their position to that carbonyl carbon. So the one right next to it is the alpha carbon. This would be the beta carbon. This is the gamma carbon. And this would be like the delta carbon and so forth, kind of using Greek letters. So if they sometimes talk about alpha carbon, that means it's basically 1 carbon away. Beta carbon is kind of 2 carbons away and so forth. And we're talking from the carbon oxygen double bond. So again, that's what we're kind of referring to when we talk about an alpha carbon, a beta carbon, and so forth. And that sometimes comes about like alpha hydroxy acids and stuff like that. That's sort of where that comes from. So then let's talk about ketones. And talking about ketones, again, our ketone group in each of these, you hopefully can see in sort of the line structure form. Here's basically our 3 carbons with the double bond, and that's basically right here in line structure. Here's basically our 3 carbon run, again with the double bond, and that is here in line structure. Also 3 carbons, double bond. And even on a ring type structure, right there's our 3 carbons with the oxygen double bond. So these are all what are referred to as ketones. We basically drop the E off for the alkane name. And for ketones which end in ONE, we put ONE at the end of it. So drop the E, put ONE. This has 1, 2, 3 carbons, which is pretty much the smallest ketone you could have. It's the smallest ketone you could have because you need 3 carbons for that functional group. So you can't have a ketone that has 2 carbons, can't have a ketone that has 1 carbon. So really the smallest one you could have is this guy. 3 carbons is based off of propane. Drop the E, becomes propanone, O-N-E, as well. This is also what is known as acetone. All right, so if you've ever used acetone or seen acetone, again, nail polish remover, stuff like that. Here we have 1, 2, 3, 4 carbons. 4 carbons based off of butane. Drop the O-N-E, is what is known as butanone. Now, when we get to about 5 carbons or more here, we do need to give the location of that carbon-oxygen double bond because potentially it could be in a couple of different locations. So 5 carbons here, based off of pentane, becomes pentanone, O-N-E. Location of this carbon-oxygen double bond, 1, 2, 3, going left to right. 1, 2, 3, going right to left. Doesn't matter in this case. So 3 pentanone. The 3, again, the location of the carbon-oxygen double bond. Here in a ring structure, that is basically 1, 2, 3, 4, 5, 6 carbons. 6 carbons in a ring is cyclohexane. Dropping that E because we have that ketone group here, becomes cyclohexanone. Much like double bond in a ring structure or something like that, you don't need to give the location. OH group as well. You don't need to give the location, but for numbering purposes, where that carbon is will be carbon number 1. In this case, we have a methyl group hanging out, which means if we go counterclockwise, 1, 2, 3, 4, 5, if we count clockwise, 1, 2, 3, so we would go clockwise to get the smaller number, and that's how we get to 3-methyl cyclohexanone. Question on that name there. Obviously, your first priority would be to give the carbon-oxygen double bond the smaller number. And once you sort of lock in that number, you then need to name everybody or number everybody accordingly. So take a second here and see what you come up with on this one. That's going to give us 5 carbons. Again, you really could go from the right and then down as well, gets you 5. Both, again, going to give you the same sort of name, a result. 5 carbons, again, with our ketone group right there, the 3 carbons and the 3 carbon run, and that double bonded oxygen right there, giving us our ketone, going to give you pentanone, O-N-E, because it's a ketone. Because it's 5 or more carbons, we do need to give the location of that group. So 1, 2 would give our carbon-oxygen double bond the smaller number. If we went left to right, it would end up at number 4. That means that's carbon 3, that's carbon 4, and that's carbon 5. So that's going to be 2 pentanone, 2 for the location of the carbon-oxygen double bond. That means at carbon number 4, we would have a methyl. So 4-methyl, 2-pentanone. Any questions on that one right there? Let's take a look at a couple here. So let's do 4-chloral 2-hexanone. Let's do 3-bromol 5-methyl. 2-heptanone. And Why don't you give that one a go, see what you come up with, and let's do. All right, see what you come up with those. So draw structures on the top and name the guys on the bottom. 3 carbon run, that looks something like that. It's a ketone. Hexane, basically 6 carbons, so that's a good place to start. 3, 4, 5, and 6 takes care of that. The 2 is where we find our carbonyl group. Again, because you're drawing it, you could go number 2 here. You could have done number 2 on the right-hand side. Both perfectly okay. So I'm going to go this way since I just drew it there. So for me, that means that this is really going to be carbon number 2. This would be carbon 1. This would be 3. And then this would be 4. And that obviously is where I would put my chlorine in that case, taking care of that. And finishing us out here in our condensed structure, that's going to be 3 hydrogens there, none there where my ketone group is at, 2 there, just 1 there, 2 there, and 3 at the end. Any questions on that there? All right, so kind of working the same approach here. Again, we see the ONE telling us it's a ketone. I see the heptane, which gives me 7 carbons. Should really pick a smaller name. 3, 4, 5, 6, and 7. Same thing here. Since you are drawing, you could put that 2 on the left, get 2 on the right. Just to mix it up, I'll go to the right on this case. So because I put it there, that would then make this carbon 1, this carbon 2, and 3, and so forth going to the left. That means a carbon number 5 from there. 2, 3, 4, 5 should be a methyl group. And that means that carbon number 3, there should be a bromol group, which is a Br. And filling in everybody with the appropriate number of hydrogens gets us something that looks like this for the condensed formula here. Any questions on that particular one there? All right, so rolling through here with the structure and doing the name. If we just go straight across, that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. You could also get 9 if you started up here and kind of went to the left. So I'm just going to kind of go this way with it and keep the one I highlighted. They're both 9. They both will get you the same thing. So 9 is based off of nonane, and that would be no, spit that out. I think that's going to be carbon 1, carbon 2, carbon 3, carbon 4 going that way. Again, if we went the other way, we could see we will have a much larger number there. So we don't want to go this way. So we'll stick with the right to left, giving us 4. And that means because of that, our methyl group, which again, is just the line there, would be at carbon number 2. 2 methyl for known and known, I believe. Yeah. Any question on that? Okay, and lastly here, longest carbon chain with the aldehyde group, right? So this is not a ketone, that's an aldehyde group. And we got 1, 2, 3, 4 if you went straight across. 1, 2, 3, 4, 5 if you went down. So that looks pretty good. So believe it or not, the longest carbon chain here is heading this way and then down. Through there. That gives us 5, which would be based off of pentane. Again, not a ketone here, so that would be pentanal. This again does not need a number, but it is carbon number 1, which means that carbon number 2, I have a bromine group. And at carbon number 3, I have a methyl group. So that's going to be 2-bromol 3-methyl pentanal. Any question on those names? Naming aldehydes, naming ketones, those things. Then let's talk a little bit about some of the properties of our aldehydes and ketones when they're in water. Remember that as we talked about, that carbon-oxygen carbonyl group is a polar group. The oxygen being more negative, the carbon there actually being more positive. So aldehydes and ketones have the ability to hydrogen bond with water between the carbonyl, oxygen, and the hydrogen there. Remember, water is polar, more negative on the oxygen, more positive there on the hydrogen of water. And that's going to give it that pretty good interaction, which is known as hydrogen bonding between a hydrogen atom and an electronegative atom, like nitrogen, oxygen, and fluorine. That makes them very soluble when they have 4 or less sort of carbons. So 4 or less carbons, pretty soluble. And again, they're soluble because they have that ability to hydrogen bond. But as we sort of build out the sides of those guys, the solubility gets less and less with water. So again, what we're talking about is pretty much as you build out more carbons and hydrogens, solubility decreases a lot. Same thing with our ketone. As you sort of build out more hydrogens on both sides, again, we get a pretty diminished effect in terms of the solubility in water. And again, it goes back to what we talked a little bit about with alcohols as well. When you kind of build out the carbon hydrogen side of these guys, you're creating a much larger molecule that has a lot more non-polar parts than, say, polar parts. And that's going to allow just something like a ketone or aldehyde here, just that one little part where it could interact with water. And again, if you put on more and more carbons, it's getting kind of hindered its ability to really interact really well. And that's what we see here. Again, fairly low numbers of carbons, 5 or less really, but 4 or less. You can see pretty soluble here in water. But as we start building up above that much in terms of carbons, again, you're just really outnumbering the nonpolar part from the polar part. So there's much more of a nonpolar part of the molecule than the actual polar part where it can interact with water through hydrogen bonding. Again, some special sort of aldehydes and ketones. That's our acetone, which is basically propanone. So acetone, you should know, is the common name for propanone. Speaking of common names for ketones, sometimes people will name ketones a very common way as well, which is very similar to what we did with ethers, if you remember. With ethers, we went to the oxygen, went to the left, went to the right, and saw what groups were there. When we're dealing with ketones, sometimes people in a common name, and again, you should only do it if it's asked for a common name, but here we go to the left, that's a methyl group. To the right is a methyl group. So sometimes a really common name people will do for this is a dimethyl ketone, which is basically propanone and also known as acetone. Formaldehyde, as you can see here, again, is our methanol. And again, that's a common name that's used there for our one carbon aldehyde group. And again, something like this guy here, if you were going to do, instead of 1, 2, 3, 4, which would be butanone, you would go, this side is an ethyl group, this side is a methyl group. This would be known alphabetically as ethyl methyl ketone. Again, that's a common name that sometimes people will still use. This name here that we've been talking about is the IUPAC name. And again, usually the name or how you want to name it when you're dealing with it. Any questions on that there? Some other important aldehydes and ketones. Here's our benzaldehyde, which basically has a benzene ring, which is this guy, and an aldehyde group on it. Hence the name benzylaldehyde. It's basically kind of what we see in almonds. Vanilla here, also an aldehyde. If you see a group here. And basically the cinnamon there basically is an we have our aldehyde over here, which should have an H on it. It's cinnamaldehyde, so it should probably have an H right there. And otherwise, it would look like a ketone in that case. All right, so take a moment here and let's identify these as aldehydes or ketones. And while we're at it, why don't you scribble down the names for each of these guys?
Professor, I have a question on the last slide.
Yeah.
So the benzene ring, the circle on the inside, could you also draw that like, because that means it's an alternating double bond, correct?
It is. It's basically because it could do a resonance structure. So really, benzene is has the 3 double bonds like you're not talking about, and
Yeah.
because the double bonds, technically you could draw the resonance structure, which just basically means move them around to the opposite locations. And again, as we talked about, very common, especially in your type of organic type book, that instead of drawing either this or this, they'll just draw that to indicate that it's sort of a double bonds moving around. Basically, they're delocalized. So you could draw it like that. You technically could draw it like that, or you could technically draw it like that. They're all technically used interchangeable.
Okay, and then where you add the oxygen double bond and hydrogen, that unit onto there, it wouldn't matter where you would.
It wouldn't matter because they're all technically the same. So if we if we looked at this and just put, say, the double bonds here, for example, basically each of these basically is one carbon with a hydrogen. So they're all equivalent. So they're all exactly the same sort of carbons. So if you drew the, like this guy like this, or if you drew it, technically speaking, badly drawn, we'll put it over here. We'll go down like that. They're exactly the same molecule because really wherever this group would be, this would be carbon 1. And then if this guy was over here, this guy would be carbon 1 as well. So they're basically the same because that functional group would get the priority.
Okay, thank you very much.
You're welcome. Let's just start with is it an aldehyde or ketone? We'll start with A. And looking at A, again, you can kind of focus in on this guy and then see what's happening to the carbon. So that this carbon, there's a carbon there and a carbon there. So that gives us our 3 carbon run with the double bond in the middle, telling us that this is definitely a ketone because of that. That also tells us that the name should end in ONE. Counted it up, 1, 2, 3, 4, tells us it's going to be butanone. And again, in this case, there's only really one place for the double bond to be, and it's always going to be carbon number 2. So you don't really need to call it 2-butanone in this case because there's really kind of no other option for it. So about 5 or more carbons is really where you need to start putting in that numbers. Occasionally you'll see some people still call it 2-butanone, but technically speaking, if the double bond was over here, it would be 2-butanone. Those are the only 2 locations you can kind of do it. Looking at B, this is our aldehyde group right there. So that tells us it's an aldehyde. And tells us also it should end in Al there at the end. And counting up the carbons is only 2. So that based off of ethane, and that would be our ethanol in this case. Coming to C, we see basically the same group there. That is our carbon, hydrogen, oxygen. Telling us also, just like B there, that it's an aldehyde. Also telling us the name should end in Al. This would be 1 carbon, 2 carbons, 3 carbons, 4 carbons straight across. You also could go 3 carbons and up would be 4. You could go 3 carbons and down would be 4. But it looks like no matter which way you go, 4 seems to be a winner. So 4 carbons based off of butane, butanol, no need to give the number here, but it is carbon number 1 for numbering our other groups that are present. And that means that we have a methyl group there. We have a second methyl group there. They're both on the same carbon. And that would give us 3, 3. Again, the number for both methyl groups location. Dash dimethyl, because there's 2 methyl groups in this compound, butanal. Any questions on that one? Remember, as we talked about many times up to this point, comma between 2 numbers, dash between number and letter in that particular case. Looking at the last one here, this is our functional group right there to there and up. Again, it's drawn in line structure, so not really put in, but this is a carbon, that's a carbon, and that's a carbon. So that's our 3 carbon run that we talk about. 3 carbon run telling us it's a ketone, going to end in ONE. This obviously is a ring structure where we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. 6 carbons in a row is cyclohexane, becomes cyclohexanone. And in this case, there's no other groups attached, which means we're good. Just like we've been talking about, because this is a ring structure, you don't have to give the location of where that carbon and oxygen double bond is. It is assumed, obviously, to be carbon number 1. Any questions on either the classification or the naming of these guys? Okay. And 2 more to finish it up and see what you come up with. We see our ketone group. Again, 1 carbon, 2 carbons, 3 carbons with our double bond there tells us it's a ketone. Looking at this, we got 1, 2, 3, 4, 5, 6 ketones, 6 carbons in a row based off of hexane, hexanone. Location of this guy going to be carbon number 2. So this would be our 2 hexanone in this case. Looking at the bottom one, we also see the 3 carbons in a row with the double bond telling us again it is a ketone. Going across here, we got 1, 2, 3, and only 4 carbons. This is not a carbon. Although people see the C sometimes and think it is a carbon, but actually not, it's a Cl. So this is actually 1, 2, 3, 4 carbons. 4 carbons based off of butane becomes butanone. Again, really do not need to give the location of this guy, but it will be carbon number 2 in this case, numbering this way, which means this would be carbon 3, this would be carbon 4, and that is actually where the group is attached. So that is going to be 4-chloral butanone. Any questions on those names or naming aldehydes or ketones or drawing them? Okay, so we're then going to talk about some reactions now that all these guys undertake. Some of us we've already sort of talked about, so we'll just kind of review some of those maybe along the way here just to make sure. We talked about the reactions. Pretty much all these functional groups or organic groups we talked about, which are alcohols, which a reminder is OH for the functional group. Our thiols, if you remember, are SH. Aldehydes being our double bond, and obviously our ketones being this guy here in terms of our functional groups. So this is basically a combustion reaction, right? It's O2 in an organic guy. That's actually ethanol there, CO2 and water, and you got your flame that happens when you do this. So one reaction that we talked about earlier when we talked about alcohols, and we'll just kind of go over them again just to make sure, is a dehydration reaction, right? So dehydration basically means removing water, right? So we're going to take out water. Water goes out kind of the way it goes on when we add water to an alkene, right? Basically, we put an OH on 1 carbon, and from a carbon next to it, we take off the H. That 2 guys right there, again, is what's going to get us our water that's going to be removed in this dehydration reaction. And once we remove that, again, you can go to the other side really and draw it identical to how it was. Just take out the water. The only deal is we're now short a bond here, so we do add a double bond between them. And again, we go from an alcohol to an alkene. The opposite here would be a hydration reaction going in the opposite direction where we put it on. A couple of reminders of this, like we talked about, remember that when we're dealing with carbon-carbon double bond and adding water, and there's an option, remember that the hydrogen goes to the carbon that started with the most hydrogens, right? The OH would go to the other guy. Remember when we're doing a dehydration reaction, going from our alcohol to our in this case, we'll do this. You know, if there happened to be a choice where I did choose this really badly here, there was no choice, but we do take it off. But if there happened to be a choice, and I actually drew it better than what I just did there, so we will leave it though. But when it comes off, right, the hydrogen goes off the carbon with the least number of hydrogens to start with, which is definitely not what my drawing shows. So that was a very bad drawing. But, you know, if we had something like this, might be a better way of drawing it. And if we were going to kind of do this dehydration, we would actually let's do this. I don't have the double bond to begin with. There you go. That's better. So if we had this option, we would take the OH from here. And when we look at this carbon, it has 3 hydrogens. When we look at this carbon, it has 2. We would take it off there and double bond between them when we do it. So putting it on to make the alcohol, like we talked about, hydrogen goes to the one with the most. Dehydration reaction, which again involves an acid usually. Sometimes they may actually give you an acid like H2SO4 or something like that. And heat, which is sometimes abbreviated with the little delta symbol, will basically take off the water again. If you have that option where you look to the carbon to the left or right of the one that has the OH, and there's a difference in terms of the number of hydrogens, we do again take it from the one with the least. Any questions on that there? We talked a lot about alcohols and really oxidation and reduction reactions, and just reminders, really kind of 3 definitions of oxidation and reduction. One is it loses electrons. One is that it gains oxygen as you go from reactants to products, and one that is it loses H2 as you go from reactants to products. Those are all definitions of oxidation. Reduction is gaining electrons, which we don't deal a lot with here in organic. We mainly deal with the oxygen and hydrogen definitions, which means it loses oxygen as you go from reactants to products, or it gains H2 as you go from reactants to products. So this is very instrumental when we were talking about really oxidation of alcohols. So we have our primary alcohol here, right? 1 carbon attached to it. When we do that, remember that what we end up doing is taking a hydrogen from the OH and a hydrogen from the carbon that has the OH attached to it. That is technically what gets us H2 on the other side. And absolutely nothing else changes in this guy. Again, you could redraw it exactly the way it is over there. You basically just take out those 2 hydrogens. And obviously here we're looking at the definition of oxidation about losing hydrogen, and we need to put a double bond there. And that gives us, again, our primary alcohol takes us to an aldehyde. again, the loss of H2 here is what we're talking about. And again, always a hydrogen from the OH and a hydrogen from the carbon are the one that's lost. By the way, the reduction reaction is the opposite reaction. That is adding H2 here. So just to show you again how that reaction occurs, if we add H2, that is like adding H. You may think, well, there must be a lot going on here, and there's not. It is just this part that happens in this reaction. So what happens in this reaction is something that happens that's very similar to when we add H2 to a double bond. If you remember, what happens is a double bond becomes a single bond, and we put an H on each of the carbons. Absolutely, positively, exact same thing happens here in the reduction reaction. Nothing else changes on this molecule, except that that double bond between the carbon and the oxygen now become a single bond. And what that does is it allows for the hydrogen to come in, one up here and one to this guy, bringing us back to our alcohol, right? Starting out our aldehyde. So this is, again, the reduction reaction, which is the complete opposite reaction or reverse reaction of the oxidation reaction of our primary alcohol. Any questions on that? We also talked about the oxidation of an aldehyde to a carboxylic acid. What's happening in this process is actually the second definition of oxidation, which is the gaining of oxygen. Where is the oxygen gained? It is simply gained right there. There is a lot more going on than just we slapped an oxygen in that spot, but for our purposes, not that necessary. But basically, once we kind of go from our alcohol, right? So we start with our alcohol here. And that's our primary alcohol. Going through an oxidation to an aldehyde. You oxidize it one more time, as we talked about, takes us to what is known as a carboxylic acid. Carboxylic acid, again, has this functional group, sometimes written out in formulas as this, same thing, basically. So oxidation, reduction would be, again, the direction here. Sometimes people just write H2 on top of there or something like that, but our reduction, our brackets and R going the opposite way. So oxidation. So primary alcohol will oxidize to an aldehyde. If you continue to oxidize your aldehyde, it will take you to this organic chemistry guy, which is known as a carboxylic acid. But one note that you should really look at all the way through here, as I've been talking about many times, is the entire structure, other than that one part, pretty much the same all the way through. You know, nothing really changes all the way through except for one little spot. So the main structure is all the way through there. So as we've been talking about, again, you got pretty much the molecule drawn for you. You just got to make sure that you understand how to change it correctly. Any questions on that?
So from the first one to the second one, it only loses the H2, but doesn't gain the O until the second to third one?
Exactly. And that's because there's, again, a lot more that happens between the second to the third one than just kind of looks like an O just pops on there. But there's actually some bonds that breaks, some water comes in, attaches to the other oxygen that provides the extra hydrogen that's needed. The hydrogen and the water come off, and eventually the net difference that occurs from like the aldehyde to the carboxylic acid is really just a net of the oxygen being added. And again, we don't get into that whole process, how that occurs. It appears like it just gets put on there somehow, but there's a lot of stuff. There's a lot of intermediate steps that happen, but the ultimate difference between it is it just gains that oxygen in that one spot always.
Okay, so like, so say in an exam, if you give an alcohol, it would just be moved to the aldehyde, or would it ask like take it through the full process of
Yeah,
oxidation?
so in most cases, if you were sort of given a problem, and say you started with this and then asked for the oxidation, it would. This is what we would be looking for. Um, if you had a problem where you started with the alcohol and then had arrows with an oxidation and then another set of arrows with an oxidation, then you would want to take it all the way this way.
To the carbonic acid. Okay, that makes sense. Thank you.
You're welcome. Other questions? So this is our secondary alcohol, which again, as we talked about as well, goes through the oxidation step of, again, losing those H2s, lost the same way as our primary alcohol that we talked about earlier. Again, H from the OH and H from the carbon. Again, that's what's going to really make H2 that would be here as well. And the rest of the molecule exactly the same, except that now we're going to, again, just like before, put our double bond in there and we get our ketone. So our secondary alcohol goes to a ketone. It does not oxidize at this point. So this guy will not oxidize. It can't really oxidize because it has no hydrogen here at that carbon. So it will not go in through any more oxidation, unlike what we saw here with our aldehyde that will go through one more kind of oxidation step. It's able to do that because technically it actually has the hydrogen that's there that allows it to do it. But once we kind of go from a secondary alcohol to a ketone, again, there's a lot more steps involved, but it's lacking that hydrogen that's sort of necessary to do that next oxidation. So that's a major difference between an aldehyde and a ketone. An aldehyde will continue to oxidize to a carboxylic acid, but a ketone will not. Any questions on that there? Obviously, just like the other one, the reduction would be the opposite reaction. Works the same way as what I was talking about previously with the aldehyde. Again, you could have this molecule and it looks like a lot of stuff going on. But when we would do the reduction reaction, it really is that double bond that's the important part. It's this part right here. Everything remains the same except for, like we did with the aldehyde, we're just going to make that double bond into a single bond. And when we do that, that's going to give us a location for really each of these hydrogens to come on. One here and one here is where it's going to come on. And we would just put it on again here and here. And again, we go back now to our secondary alcohol, starting from our ketone. And again, that is the reduction reaction that's occurring. Oxidation, again, takes us from secondary alcohol to ketone. Reduction takes us backwards from our ketone to our secondary alcohol. Any questions on that there?
Would you have to add that H2 at the end?
You mean here?
Yes.
Technically it's there. This is probably for our purposes the more important part of it, but technically the H2 is there. So it's a good idea. I personally wouldn't probably take off anything as long as you have the ketone structure correctly. But it definitely is being produced. Yeah.
Okay.
Other questions? And again, sometimes it's helpful to put it there in case you're asked about the reduction one. You could kind of visualize what's going back the other way. It kind of gives you what's going to react in the reverse reaction, that kind of reduction reaction. Now, we also talked about the tertiary alcohols, and again, does not go through oxidation because really for that, you need those hydrogen, and it has no hydrogen here. So because it has no hydrogen, a tertiary alcohol, again, will not go through any type of oxidation reactions. Any questions on that one there? So here's again methanol, which is a primary alcohol. Goes through our oxidation, gets us to our aldehyde. And again, from our aldehyde, oxidizing one more time, gets us a carboxylic acid, which is known as methanoic acid. And again, the differences here as we go from one to the other. This is our loss of H2. This is our gaining of oxygen as we go through there. And then just to give you a hint in terms of naming, methanol, which is our alcohol name, methanol, which is our aldehyde name. This is also based off of one carbon, and it's a carboxylic acid. This is what is known as methanoic acid. We name carboxylic acids like that, oic acid at the end. Drop the E and put OIC, ethanoic acid, methanoic acid, propanoic acid, and that's how we name a carboxylic acid. Again, based off of one carbon, based off of methane, and carboxylic acids ends in oic acid. Ethanol, same deal, sort of happening here in this particular case. Any questions on that? Again, our primary to our aldehyde, and really our aldehyde here into basically carboxylic acid, which will basically break apart into CO2 and water. So it's a slightly different one because of what you'll end up with in the end there. All right. We also, I think, talked about the oxidation of or the reaction of thiols. Remember, for thiols, you do need to know the functional group, which is our HS, right? Makes it a thiol. Has very similar sort of properties kind of to OHs. It does go through an oxidation, and the oxidation here is, again, the loss of H2. So basically what happens when it goes through this oxidation reaction, we have a thiol to the left, a thiol to the right, a long protein chain it's on. But basically, we're just going to take out the H2 in the oxidation here. And when it does, we basically then just slap those two guys together, both sides. It makes what is referred to as a disulfide bond or bridge. And that is something that we see a lot in proteins as well. And it's a very simple reaction in the sense of you just have, don't matter what the sort of thiols look like. You know, say we have something like this, plus maybe even a smaller thiol going in this direction. Basically, what's going to happen is once it goes through that oxidation reaction, these two H's basically come out, and that makes H2. And then pretty much all you have to do is go left to right and put them together, take out the H's. So if you just start left to right, you got CH3, you got CH2, you got CH2, you got an S. We take out the two H's to our disulfide bond, and there we go. Yeah. And that is our oxidation reaction. I'm imagining you might even be able to figure out here the reduction reaction, which is the reverse. What happens in the reduction reaction? Well, we add H2 back in. Where does it break? Right there. So going in the opposite direction, doing that reduction reaction, if we started with this guy, with our disulfide bridge here, our bond, and we added H2, we simply go left to right and then break it right there and put an H on each of them. So we would go left, and now we're going to add the H, and then we would add the H to the other side and finish it up with this guy. So again, that oxidation reduction, basically reverse of each other's there when we look at those guys. Any questions on that there? Okay. Here's some behaviors of sort of alcohol and blood alcohol levels, obviously with ethanol, and you could test it with a breathalyzer sort of test. But let's finish up here talking about a couple of important tests that help us recognize a aldehyde being present versus a ketone. And one of those tests is what is referred to as the Tollens test. The Tollens test is basically a test that uses what is referred to as a Tollens reagent, and inside there is a silver ion with a +1 charge, and it will oxidize aldehydes and not ketones. So here's our aldehyde. This guy is actually going to go through reduction. When it goes through reduction, it gains an electron and it becomes silver on the other side. In the process, when somebody gets reduced, somebody else gets oxidized. So our aldehyde here will get oxidized, and as we were just talking about, when we oxidize an aldehyde, we end up with a carboxylic acid. And what is the difference between our aldehyde and our carboxylic acid? It is the O we were just talking about. There's absolutely no other difference between where we started here and where we ended up over here, other than that O that's right there. So in this process, using the Tollens reagent, we know that we started with an aldehyde because it turned positive. How do we know it turned positive? Well, when the silver gets reduced, it makes silver. It looks like this, yes. Sometimes referred to as the mirror test because it makes sort of that mirror silver type color in the test tube. And that would be a positive. So what would that tell you? It would tell you that you started with a aldehyde. Why do you know that? Because we just talked about a ketone. What happens when we try to oxidize a ketone? We get no reaction, which means we would get no reaction and the silver would not become that really dark silver color, and it would be a negative test. So if you ran this test and you did not get this silver color, that would imply that you started probably with a ketone versus an aldehyde, if those were obviously your only two options. So if you had to choose between an aldehyde or a ketone and you did this test, it turned silver, positive for an aldehyde because that made our carboxylic acid. If you did this test and it was negative, it didn't turn that silver color, then that would imply that you had a ketone because it will not go through an oxidation to a carboxylic acid. Question on that? Again, looking at our name, this is a 2-carbon, which is known as ethanol. And our carboxylic acid, as I said before, has the OIC acid. So ethanol becomes ethanoic acid is our name of a carboxylic acid that is formed. So that is one test that we could use to distinguish between an aldehyde or a ketone. Another one is what is known as the Benedict's test, which again will distinguish between an aldehyde versus a ketone. In this case, kind of similar, we actually go with a copper ion, copper 2, kind of blue in color. And through this process, it also gets reduced to basically copper 1. Copper 1 oxide is kind of like a, I'll say orange, it says red, but most of the time it turns out kind of like an orangey brown color, but technically like a brick red color. And what we're looking for here in the test tube is for our test tube to go from blue to like a orangey red color, we'll call it. More of an orange color in most cases, orangey red type color. And if you do that, that again means that we had a aldehyde and not a ketone. And that's because here's our aldehyde, again with our group. This getting reduced means this guy is getting oxidized. And as we talked before, our aldehyde will get oxidized to a carboxylic acid. Remember, again, the ketone will not go through that oxidation, but here going from our aldehyde to our carboxylic acid. So again, if you see your test tube go from blue to this orangey type color, that is a positive test, meaning, yes, I did start with an aldehyde. If your test tube started blue and stayed blue, that means no oxidation occurred and you had a ketone. So again, for both of these tests, any type of positive reaction would mean you had an aldehyde. Any type of negative reaction or nothing really occurred would mean that you started with a ketone. Questions on that there? Here's some pictures of the test tube, and again, in my experience, it's more orangey, grossy looking color, but it gets that same thing. So same thing happening here. That's an aldehyde group at the end of this carbohydrate, and here's our carboxylic acid. Again, the oxygen being inserted here. We would do this, we would see that orange, it would tell us that it is a aldehyde that we started with and definitely went through. Any questions on that? So those are two very popular tests to identify whether or not you started with an aldehyde or a ketone. And again, if the test was positive, right? So you weren't sure, maybe you kind of knew what you started with was a 5-carbon something, and you did this test and it ended up positive. So what that would mean is if you started with a 5-carbon guy, you should actually have an aldehyde, right, to start with, because it would have been positive. And let's say you did the same test with a 4-carbon guy and it was negative. That means that you started with a ketone because it ended up being negative. So that's how you, again, can use these tests and sort of back figure it out. Did you start with a ketone or aldehyde? Those are usually two very common groups that are sort of looked at. Any questions on that there? Okay, so we'll stop there today. We're essentially done with this chapter. We'll finish the last couple of slides next time, and then we'll kind of be done with this chapter. We'll roll into the last organic chapter on Wednesday. Other than that, as I mentioned last time, exam has been obviously postponed to next week, and it obviously will cover through the rest of this chapter, which we'll finish on Wednesday. And then that should be it. We're getting close to the end there, I think. All right, so we'll stop there.